Welcome to Conceptual Physics at Delaware Tech, Chapter 22, Electrostatics. So electrostatics, the name means electricity and static. Static means staying still. So we're talking about charges that are in one place or near each other but not moving. However, we use the term electrostatics to include movement frequently. All right, so we'll talk about electrical forces and charges. We'll talk about the concept of conservation of charge. We'll talk about Coulomb's law. And then we'll talk about some definitions of terms, conductors, insulators, and superconductors, as well as semiconductors. We'll talk about charging. This is the creation of charge on an object or changing one object that doesn't have charge to an object that does have charge. We'll talk about charge polarization. This is separating charges, taking a neutral object and changing it so that positive charges on one side of it, negative charges are on the other. And then we'll talk about three related terms but are easily confused. We'll talk about electric field or electric field strength, abbreviated E. This is a force per charge. We'll talk about electric potential energy. This is an energy. This is the energy of something being in a certain position. And then we'll talk about electric potential, which is also known as voltage, an abbreviated V. So this is the amount of energy per charge. And these are all related, but they're really easy to be confused with each other. And then finally, we'll talk about storage of electrical energy using a device called a capacitor. So electricity is a general name given to a wide range of electrical phenomena. You've all seen lightning. You probably noticed a spark when you strike a match, and the movement of electrons in circuits. Now, the fact is you can never see electricity, but you will often see the effects of electricity on the matter around it, as in lightning. Lightning is electricity coming through the air from the clouds down to the ground, but in the process it's ionizing air along the way, and that creates that mini explosion as it's coming down. So it's really not the electricity you're seeing, it's the effect of the electricity on the air molecules being ionized. And the same thing happens when you're looking at a spark from a match. You're ionizing particles in the air. And the movement of electrons in a circuit, you can't see that, but you can see how electricity is used to turn on devices like lamps and appliances. All right, so electrostatics, as I mentioned, involves electric charges. And technically, it means the forces between charges that are at rest. But we frequently use the term electrostatics to mean the study of charges even when they're not at rest, when they're actually moving. And that aura around any electric charge, around any positive charge or around any negative charge is referred to as the field, the electric fields. And we've already seen that there are gravitational fields around any object with mass, and these are essentially lines of field lines that are really a combination of force lines that are strong when they're close to the object and weak when they're far back from the object because of the inverse square rule about distance. And we've talked about that, how the force of gravity gets weaker with the distance squared. Well, the same thing is true of electricity, and the same thing is true of magnetism. The further away you are, if you double the distance, you double squared its decrease in the force. And we'll talk more about that later. So electrostatic also includes the behavior of materials that have charges. So just as a general rule of electricity and electrostatics, opposite charges attract one another. A plus charge and a minus charge will attract one another, as shown on the right here, whereas like charges repel. Positive to positive will be repelled away from each other. The force lines are away from each other, and negative to negative, it's the same thing, away from each other. So negatives repel, like charges repel, and opposite charges attract. So the particles in the atom have different charges in them, and the protons, which are found in the nucleus, with the neutrons, the protons carry a positive charge. They carry a unit charge, so we call that a charge of +1 for each proton in the nucleus. And positive charges attract the negative charges from the electrons, and they repel other positive charges that are around, or even positive charges in the nucleus. Now you may wonder, why are all the positive charges clumped together in the nucleus if they all repel? Well, they do all repel, but there's another force that's stronger than that holds them together at close distances. We don't cover that force in this class. It's called the strong nuclear force, but that's what holds the protons and neutrons together. But the fact is, positives will repel positives, negatives will repel negatives. And the electrons are buzzing around in a cloud of space surrounding the nucleus, and that makes up the volume of the atom. So most of the mass is in those protons and neutrons, and all the positive charges are in the protons. The electrons carry all the negative charges, and they are moving all around. They're point charges that can be anywhere in a volume of space around the nucleus, and they have unit negative charges. So each one has a charge of -1. The neutrons, as the name suggests, are neutral. They don't have any electric charge. They're involved in the strong nuclear force to hold the nucleus together, but that is unrelated to charge. The neutrons will not attract or repel positive or negative charges. So, fundamental facts about atoms. Electrons are really the particle that we're going to be mostly interested in. And every atom is composed of both the positively charged nucleus, and it's positively charged because of all the protons in it, surrounded by negative charge cloud of electrons. Okay, these are all the electrons. It could be one electron, it could be as many as 118, depending on the atom. But there are all these electrons around, occupying the volume of space around, and that's the source of the negative charge. And every electron in any atom has exactly the same quantity of charge, but it's negative relative to the positive charge of a proton. It's just that while every electron has the same mass, that mass is much, much smaller than the mass of either a proton or a neutron. So protons and neutrons, they compose the nucleus. We've already said this. Protons and neutrons they're a little more than 1,800 times heavier, more massive than electrons. So the vast majority of mass in an atom is from protons and neutrons. All the positive charge is from the protons, all the negative charge, and the volume of the atom is from the electrons. And an atom, by definition, is a neutral particle. If it's not neutral, we frequently will still call it an atom, but we also call it an ion. And we'll talk about that in the next slide. So an atom, by definition, will have an equal amount of positive charged protons and negatively charged electrons. The neutrons have just slightly more mass than the protons, but absolutely no charge. So they really won't be talked about much in the rest of this unit. So atoms usually have as many electrons as protons in order so that the whole atom has a net zero charge. It could have one proton and one electron, one positive charge, one negative charge, or it can have 50 positive charges and 50 negative charge, 50 protons and 50 electrons. It can have 118. That's the biggest atom that's ever been made. So ions, as I mentioned, are atoms or molecules or other particles that have a charge, a positive charge or a negative charge. It could be +1, +2, +3. It could be -1, -2, -3, etc. Whatever it is, it's in unit numbers of charges. And the atoms get their charge by electrons either being lost or gained by the atom. Atoms don't typically lose protons to change their charge. When that happens, the atom changes what kind of element it is, and that only happens in nuclear reactions, and we're not going to talk about it in this unit, and we really don't cover that in this course anyway. So when we're talking about atoms becoming charged, they are becoming charged because you're either gaining negatively charged electrons or you're losing negatively charged electrons. So a positive ion is an atom that has lost at least one electron. Remember, the electrons carry the negative charge, and I remember when I was first learning this material, it took me a while to wrap my head around the fact that I have to keep track of negative charges instead of positive charges. Remember, it's the electron is a unit of negative charge. So when it goes away, you're leaving behind a positive charge. If you don't have as many electrons as you have protons, you're missing electrons relative to the proton number, and therefore you will have a positive charge. If you have extra electrons relative to the number of protons, that would be a negative charge, and that would be a negative ion. We have names for them in chemistry. Positive ions are called cations, negative ions are called anions. We're not going to use those terms here, but in case you see that, that's what those are. So a negative ion has gained one or more electrons, or it could be just an electron itself. We don't always call it an ion, but it is a negatively charged particle. So electrons in atoms come in two basic categories. The innermost electrons, sometimes called the core electrons of an atom, and the outermost, also called the valence electrons. So the innermost electrons are the ones that are closer to the nucleus. They're being pulled in by the positive charges of the nucleus, kept into a smaller volume of space, and they're really held on tightly to the atom, and they rarely come off of the atom. But the outer electrons, the outermost electrons, frequently called the valence electrons, especially when you're in chemistry, those are more loosely attracted to the nucleus. They're further away from the nucleus, and therefore there's less of an electrostatic attraction between the positively charged nucleus and the negatively charged electrons that are far away from the nucleus. So they tend to be able to be kicked out pretty easily. It doesn't take too much energy to pop an electron off of an atom if it's one of the outer electrons. And there are some atoms that love to lose their electrons because it helps stabilize them in certain ways. That's more of a chemistry thing than a physics thing, but that's what happens. And metals love to lose electrons. They're much more stable they're very stable when they lose electrons to become positively charged ions. And that is why metals tend to conduct electricity very well, because they can donate at least one electron each into the sea of electrons, which can become the electrons that move in electrical currents. And we'll talk more about that in the next unit. So electrons in atoms, you can actually make electrons move from one group of atoms to other group of atoms with everyday movements by literally taking a comb and going through your hair. And I don't have much hair to do it for you. But if you take your comb and go run it through your hair or brush through your hair, the electrons will actually transfer from your hair to the comb, and especially when you're combing dry hair. When you're combing dry hair, it's amazing how easily those electrons jump from your hair to the comb, and the comb will pick up those electrons, and your hair will lose those electrons and become positively charged. The comb will become negatively charged because it has an excess of electrons. And you can do the same thing with other items that aren't exactly household items, like if you had a glass rod and some silk cloth, and you could literally take a glass rod and rub the silk cloth over the glass rod, and now the electrons will jump from the glass rod to the silk, and the silk will become negatively charged because it has an excess of electrons, and the glass will become positively charged. Now, when I say there's an excess of electrons, it's not a giant amount of electrons. If I said a million, a billion, a trillion electrons, that sounds like a lot, but that's actually a very small amount compared to the number of atoms in each of these things: the silk rod, the silk cloth, and the glass rod. It's a tiny, tiny fraction. If you were actually to remove even a tenth of the electrons, to ionize even a tenth of the atoms in either one of these, you would get an enormous explosion. So that never happens. You're just removing a small fraction, but because atoms are so tiny, it turns out to be a large number of electrons, just not a giant amount of charge. So when you brush your hair and scrape electrons from your hair to the brush, the charge of your hair is A, positive, B, negative, both, neither. Well, we know that the electrons are jumping from the hair to the brush. The electrons carry a negative charge, and therefore the hair will end up becoming positively charged because they're losing electrons. They're losing negative charges, so they're leaving behind an excess of positive charge. So if electrons were scraped off onto the brush, the hair would lose that negative charge, the hair would become positively charged, the brush would become negatively charged. All right, so conservation of charge. What this is saying is that if you have something happening and then you have a situation after that happened, if you looked at the whole charge beforehand, added up all the positives and negatives, you would end up with exactly the same total of positive and negatives at the end. So if I started with an excess of negative charges and I did something and maybe I created some positive charges, I would have even more negative charges to counteract that. So my total of negative would still be the same. A more common situation is if I start with 0 charge and I do something to split that charge. So I have two objects that each have 0 charge, and then suddenly I have two objects and one of them becomes negatively charged and one of them becomes positively charged. But if I added up all those charges together, it would be 0, what I started with. If I had an extra negative here and did something, I could move charges, move the negatives, but I'll still have extra negatives over here. If I have extra positives and do something, I'll still have extra positives later. Charge number does not change, and the reason is because electrons are not created and they're not being destroyed. They're just being moved around. And the example shown here is with an amber rod instead of a glass rod. Amber is just fossilized tree sap. And the ancient Greeks actually did this over 600 years BCE. So this was 2,600 years ago. There was a Greek who was living in what is now Turkey named Thales of Miletus. And Thales took an amber rod and fur and he rubbed it and he saw that there were charged effects where things were attracting. Now, they didn't call them charges and they didn't say positive and negative, but they knew something was going on. Well, eventually, years later in the 1700s, when Benjamin Franklin was studying electricity, he was also looking at these kinds of transfers and realized that it was two different things. One he called positive and one he called negative. And unfortunately, he guessed wrong about what was in currents. He thought it was the positive charges. And to this day, when you write currents, you consider how positive charges are moving around the current, around the wires in a current, even though we know for a fact it's negative charges going in the opposite direction. So it becomes very confusing, and no one ever decided to change it, even though we know it's absolutely wrong in direction and wrong in charge, but it still has the same effect of going one way with positive charges is exactly the same results as if you had negative charges going the other way. So we're kind of stuck with it now. But it turns out the ancient Greeks who were looking at this with amber rods and fur or silk, when electricity was later studied, they had to name it. Well, since some of the first things to study electricity were with amber rods, they named it after amber. And the Greek word for amber is this word. But if I change these Greek letters into Roman letters, the ones we use in the English language, it's the word electron. Now, this is not the same as the particle electron, but this is the word that we named electricity after. It's also the word that we named electrons after, or electrical, anything that sounds like that. Electrostatic, electricity, electrons. They were all named after amber because this was one of the early sources of electricity that was studied. Now, this was 600 years before BCE, but the fact is, the ancient peoples, even 2,000 to 3,000 years ago, knew about something that was electrical, like from electrical eels that were in water that were near the Egyptians. They were aware of electrical eels, so they were aware of something that had similar properties thousands and thousands of years ago. But it really wasn't decided what it was until the 17 and 1800s when it was named electricity, and when people started referring to actual positive and negative charges. So in any case, with conservation charge, if you have something and at first the amber rod doesn't have a charge and the fur doesn't have a charge and you rub it, the amber rod literally will steal negative charges, steal electrons from the fur, and the amber rod will become negatively charged with those excess electrons. And there are question marks on the fur here in this drawing. But as you know now, because the fur has lost electrons, it now has a positive charge. But the total charge is still 0. We conserve charge. No charges are created, no charges are destroyed. They're just moved around. All right, so Coulomb's law. Coulomb's law was worked out by Charles Augustin de Coulomb. A Frenchman living in the early 1700s, and I'm sorry, the mid and late 1700s and the early 1800s. And what Coulomb noticed was there was a relationship between electrical force. This is the attraction of opposite charges or the repulsion of same charges, like charges. He noticed there was a relationship between that and how great each of the individual charges were, as well as the distance between the centers of the charges. Now, at this point, you might say, hey, wait a minute. We saw something similar with gravity. Newton's law of gravitation was almost identical. That was a force that was based on how much each of the masses were and the distance between the centers of the masses. And in fact, the formula is nearly identical in the way it looks, and we'll show that in a second. So what Coulomb realized is that for a pair of charged objects, and if they're the same charge, it's a repulsion force. If they're the opposite charge, it's an attractive force, okay? But the amount of force is proportional to each of the charges individually or to the product of the charges. You multiply the two charges, it's proportional. So if I double one charge, I'll double the force. If I double the other charge, I'll double the force. If I double both the charges, I will quadruple the force. I'll multiply it by 2, and then I'll multiply it by 2 again. If I triple one force and double the other, I'm sorry, if I triple one charge and double the other charge, I will triple the force and I will double the force. So 3 times 2 is 6-fold. I will increase the force by 6-fold, not 5, 6. We multiply those numbers together. Likewise, the force is inversely proportional to the square of the distance. This is the famous inverse square rule that we already saw for gravity, and we see for electric force, and we will also see for magnetic force. The further away you are, the force weakens much faster than the distance increases. The force goes down with the square of the distance. So if I triple the distance, I will decrease the force 9-fold, 3 squared. If I increase the distance 10-fold, I will decrease the force 10 squared fold, 100-fold. So by moving charges away from each other, I can make the force go down dramatically. That's either attractive if they're opposite or repulsive if they're the same charge. So if charges are alike in sign, that force value, it's repulsive, and if they're opposite in sign, the force is attractive. We can assign signs to it, plus and minus, but we're not going to for this course. We're just going to look at the magnitude of the forces and just keep in mind whether it's an attractive force with opposite signs, with a positive and a negative, or it's a repulsive force pushing the charges away from each other if they're both positive or if they're both negative. So the formula, using this proportionality relationships we just looked at, we know force is proportional to Q1, first charge. Charge is abbreviated with Q, by the way, lowercase q. So the first charge is Q1, the second charge is Q2. So force is proportional to both of those, so those are in the numerator. And force is also inversely proportional to the distance between the charges squared, so that's in the denominator. So the only thing we're missing to make a proportionality and equality is to just shove in a constant that will make everything exactly equal. And just like with gravitation that used the big constant g, let's see if there it is right there. So for Newton's law of gravity, we did the same thing. We had masses on the top, we had distance squared on the bottom, and we threw in g, the big constant, the gravitational constant g, to make this an equality. Well, we do the same thing with k, the Coulomb's constant here, to make this work as well. And it's just 9 billion, 9 times 10 to the 9 billion Newton meters squared per Coulomb squared. Now, Coulomb is a unit of charge. Now, remember I said an electron has a charge unit of 1 charge, and a proton has a unit of 1 charge. The electron's -1, the proton is +1. Well, a Coulomb is a lot of those charges. A Coulomb is 6.24 times 10 to the 18 electron charges, or if it's positive, proton charges. Same thing. It's the same amount of charge, just a different sign. 10 to the 18, that's a quintillion. So it's 6 quintillion charges from electrons, or 6 quintillion electrons. That's the amount of charge in 1 Coulomb. So a Coulomb is a big amount of electrons. Okay, it's a big amount of charges from electrons. So keep that in mind when we're talking about a certain amount of coulombs. So it's 6 times 10 to the 18 charges that make up a single coulomb of charge, and that's the unit we use for charge. The symbol is Q for charge. The unit is capital C for coulomb. And the fact is, these charge-charge attractions and charge-charge repulsions are what underlie atoms coming together that are attracted to one another. They're attracted because the electrons are being shared between two different atoms' nuclei. The nucleus, which are positively charged, you have the shared electrons, which are negative, and that helps pull them in together. Otherwise, you wouldn't be able to pull a positive nucleus with another positive nucleus. They'd be repelling. And the electrons kind of form that electrostatic bridge that pulls them all together. They don't come in too close because now the positives will be too close to the other positives. So there's a balance between the attractive forces of the opposite charges and the repulsive forces of the like charges. All right, so according to Coulomb's law, a pair of particles that are placed twice as far apart will experience forces that are, now, you'll notice I didn't say if they're like charges or opposite charges. It doesn't matter. If they're like charges, this will be a repulsive force, and the rules still work. If they're opposite charges, it'll be an attractive force that's pulling them together, and it's still a force that is dependent on how big each of the charges are and the distance squared in the denominator. It's an inverse relationship. So if we're suddenly placing them twice as far apart, we're doubling the distance, but the force is related to distance squared. If I'm doubling the distance, doubled squared is 4 times as big an effect, but the effect is inverse relationship. So if the distance goes up, the force will go down 4-fold. So it's 1/4 as strong. Separating the charges away from each other by just doubling, here it might be the old distance, now we double the distance, the force goes down 4-fold by doing that. So electrostatic force, just like gravitational force, just like magnetic force, is inversely proportional to the square of the distance between, in this case, the charges. With gravity, it's the distance between the masses. With magnetic fields, it's the distance between the magnetic poles. So a 2-fold increase in distance will be a 2-fold squared or 4-fold decrease in force. One goes up, one goes down, but force is affected more than distance by the square of the distance. All right, so Coulomb's law and the gravitational law have a lot of similarities and a couple differences. Let's talk about those. So in terms of attraction, electrostatic forces, as we already know, can either be attractive, and we call the force negative when they're pulling together, and then they're positive when they're repelling each other. The reason why they use the positive for repelling, it's the amount of force to bring them together. And when they're already attractive, it's a negative force. So you don't need to bring them together. They're already coming together. So it's negative force to bring them in because they're already attracting. You don't have to worry about that. But gravitational forces are only attractive. Normal gravity is only attractive. More mass will bring them together. There's no anti-gravity. However, there's a little star here, a little asterisk, because we don't know much about the nature of dark energy, and dark energy may have an opposite of gravity, an anti-gravity effect, but that is way beyond the scope of this course. I'm just telling you because someday maybe people will figure out what it is, and then you'll find out that there really is an anti-gravity in some point. But right now, we can't definitely say that there is. So we'll consider gravity as being purely attractive for now. All right. And the other differences and similarities are the proportionality. Electrostatic force is proportional to each of the charges as well as the product of the two charges, Q1 and Q2. While gravitational force is proportional to each of the masses, mass 1 and mass 2, or the product of them, mass 1 times mass 2. So very similar, just using masses for gravity, charges for electrostatics. And the forces both have the same inverse square rule for distance and force. You increase the distance whatever change in distance, it's that change squared will happen to the force, but in the opposite direction. So if I increase the distance, I will decrease the force dramatically. If I decrease the distance, I will increase the force dramatically to the square of the change in the distance. All right, charge polarization. So charge polarization is when you take an object that doesn't have any net charge on it. All the positive charges and all the negative charges equal each other. It's totally neutral. But polarization, as the name might suggest, is we polarize the object so more of the negative charges end up on one side of the object and more of the positive charges end up on the other side of the object, just slightly. But it doesn't take much to have a lot of electrons, because remember, atoms are super small, so even a tiny fraction of atoms that are polarized will result in a significant amount of total charge. So this movement, so you have this slight excess on one side and slight excess of the other charge on the other side, this is referred to as polarization. And this can happen within an atom, it can happen within a molecule, it can happen with a giant molecule, it can even happen with big objects like a balloon, or even something bigger and heavier than a balloon. And so if you rub an inflated balloon on your hair or on a rug or something wool, you can move charges on the cloth or whatever it is you're rubbing, or your hair, and have the electrons jump to the balloon and negatively charge the balloon. Now the balloon is made of rubber usually, and rubber is not a good conductor. So, and we'll talk about what that means later, conductors and insulators. It's an insulator, and what that means is when you put a charge on it, it just stays there. It doesn't move all around. So if you're rubbing a balloon, the side you rub is going to get some extra electrons, and the other object that's being rubbed will have lost those electrons, and those will be donated to the balloon. So I'm going to stop this for just a second, and I'm going to grab a balloon, and I'm going to show you how this. Okay, so I'm back. So I've taken a balloon and I've rubbed it against my grandmother's Afghan that she knit for me a long time ago. And hopefully we've transferred some electrons from the Afghan to my balloon. And I'm going to put it on the wall here. I hope it sticks, and there it is. Now, why is it sticking? Well, I didn't charge up the wall. Why would negative charges stick to a neutral wall? Well, the reason is, when I put this balloon that's now negatively charged next to a surface, any surface, the atoms that make up the wall, they have electrons in them, and when that negatively charged balloon approaches the wall, the electrons kind of move away from it. They're being repelled. The ones in the wall move away. That's a repulsive force. And the atoms stay behind and are attracted to it. The positive charged portions of the atoms stay behind. So we end up polarizing the wall. Now it's much narrower than this drawing implies. It's subatomic scales where we get this polarization. Each atom is slightly polarized, where the electrons tend to be on the far side away from the balloon, leaving the nucleus closer to the side that's near the balloon. And you end up with this attraction because we've induced a polarization in the wall. We created a polarization in the balloon by friction and transferring electrons from the Afghan, from this cloth here, to the balloon. But then when we put the balloon on the wall, the balloon has induced polarization on the wall. So it's two different methods of polarization. We have a friction and contact from rubbing the balloon on the cloth, followed by the balloon polarizing the wall. Well, once it's polarized, the positive part of the wall is now attracted to the negative part of the balloon, and that's why the balloon is staying up there. And this works much better for smaller balloons because they just weigh less, and you're not fighting the force of gravity quite as much. We'll see how long that stays there. Hopefully that won't be too distracting. But this is the whole idea behind polarization, a charge polarization of objects by friction, and then later by induction of new polarization. So let's talk a little about conductors. I mentioned conductors and insulators earlier. Conductors are materials that have electrons in their outer shells that are not attached very tightly to the nuclei of the atoms they're associated with. And in fact, the best conductors almost donate electrons into the sea that surrounds the atoms, and these can be free to wander through the material, especially if a current is induced by putting some voltage on a wire that's made of something like metal, and then making these electrons flow through the body of the wire. But it doesn't have to be exactly like this. And there are lots of different substances that will act as conductors. We already know that a lot of metals can work as conductors. The most famous one is copper. Most people know about copper wire. But the fact is, silver is actually the best conductor of all the metals. Gold is also an excellent conductor. And the reason why is when you have solid silver, solid copper, solid gold, they tend to donate roughly 1 electron per atom into the sea that surrounds them. I'll take this down. This sea of electrons that surrounds the atoms, holding the atoms together. So it's not like a single bond between atoms. It's a sea of electrons that act as this big smeared bond holding the metal together. That's why metal is so strong, because of this sea of electrons. But it is also the reason why metals are such great conductors. They all donate electrons into the sea, and if you put a voltage across this metal, the electrons will flow in a current. And we'll talk more about that in the next unit. But this will happen in metals like silver, copper, gold, iron, aluminum, anything that includes iron like steel. But it will also happen in certain liquids that contain ions, that contain charged particles that can also move. So these will act as conductors as well. And this includes salt water, shown in the bottom here. You put salt in water, it breaks up into its component ions, sodium positively charged ions and chlorine negatively charged ions called chloride ions. And these can respond to charge attractions. If I put a positive charge on the right and a negative charge on the left, the negative charges in the liquid would flow to the right towards the positive charge, and the positive charges would flow to the left towards the negative charge. In the case of copper, the only charges that are moving are the electrons. The copper ions stay still in the wire, and the electrons will move towards the positive charge. That might be from a battery or a generator. All right. But we also have substances like insulators, and insulators are almost the opposite of conductors. Their electrons are very tightly bound, and they don't really donate them to become part of current and carry charge. However, that said, every insulator, if you pump enough charge on it, it'll start behaving like a conductor. So the most famous insulators would be rubber, glass, plastics, cloth of any kind of fabrics, air, wood, especially if it's dry wood. Wet wood's another matter. That can carry, that has some ions in it, and that will carry charge and electricity. Diamond, oils, fats, non-metals, ceramics, asphalt, and super purified water that has been cleaned of almost all the ions possible. It's impossible to get rid of every ion in water because it makes its own ions. But super purified water is a very poor conductor of electricity. In fact, that's one way they check the purity of water. They look for how good a conductor it is. If it's a terrible conductor, they know they've got really pure water. But these things don't carry charge very well. When the charge is put on an insulator, it stays in one place, and this rubber balloon is an insulator. So when I put charge on it, I put charge on one side by rubbing it on the cloth on one side. If this was a conductor, the charge would immediately surround the whole thing. It would spread out all over the surface of the balloon. But since this is rubber, it's terrible conducting charge. When I put charge here, it just stayed there. If I tried to turn the balloon around and put it on the wall, it wouldn't have worked. I have to use the same side that I rubbed to go onto the wall, because that's where the charge was created. That's where the charge will stay. So semiconductors are kind of an interesting material. These are materials that act sort of halfway between insulators and conductors. And under the right conditions, they can be made to switch between behaving like an insulator that doesn't carry charge very well and move charge very well, to conductors which move charge extremely well. And because of that, you want substances that are somewhere between metals that are excellent conductors and non-metals that are excellent insulators. And the substances that are most often used to make semiconductors, these are the semiconductors in your semiconductor chips, your transistor chips. They're made with the semi-metals, also known as the metalloids on the periodic table. And this is that diagonal line that starts with boron and silicon, goes through the right side of the periodic table. And that includes silicon, boron, germanium, arsenic, antimony, some people call it antimony, but antimony, tellurium, and sometimes selenium is included in that group. And these are your substances, your elements that have properties sort of like metals and sort of like nonmetals, sort of like conductors, sort of like insulators. And under the right conditions, they can be driven to act in both ways, depending on how they're manufactured and what they're mixed with. Typically, you will take a substance like silicon and dope it, which means add intentional impurities to some silicon to make it carry negative charges, and then dope it with some other elements to make a different part of the silicon act like positive charges. And you can have current going back and forth between it, and you can activate it under the right conditions. So they can act as insulators when they're absolutely pure, but if you add these impurities, you can make them behave like conductors. And semiconductors will also conduct electricity when light shines on them. So if you take any of these semiconductor composites, shine light on them like selenium plate, this is not exactly a classic semiconductor, but it is one that's used in solar energy. If you hit light with the right wavelengths, with the right frequency of light hitting it, it will activate the electrons in there to cause it to generate electricity. And the charge will leak away from the areas, only the areas exposed to the light. All right. When you buy a water pipe in a hardware store, the water isn't included. All right. So we're using what's called the water analogy, the water flow analogy of current. And we'll talk much more about this in the next unit. When you buy a copper wire, however, the electrons, okay, so the idea is when you buy a pipe, the thing that flows through the pipe is water. It doesn't come with the pipe. You have to purchase the water and have the water flow through your pipes. So what is flowing through the copper wire when you have electricity? It's the electrons. So where are the electrons coming from? A, they must be supplied by you just as water must be supplied for a pipe. B, they're already in the wire. C, they may fall out, which is why we insulate the wires. Or D, none of the above. Well, the electrons are already part of the copper. And in fact, every part along the circuit has atoms, and all the atoms have electrons. Most of the electrons will come from the wiring itself, from the copper, and copper is really good at donating the electrons. You might get some electrons being donated from the chemicals in the battery, or the generator, or the lamp, but the bulk of them will come from the wire itself. Copper loves donating 1 electron per copper atom into the sea of electrons, which will flow to become your current. So the source of electrons is the material in the circuit itself, the copper wire in this case. So it's already in the wire. Conductors, like copper, they're materials that have 1 or more loosely bound electrons in their outer shell. They're very loosely bound from the nucleus, and as a result, they're free to flow through the material as you find in electrical current. Superconductors, all right, so we talked about conductors. These are things that donate electrons that can flow as current. The flow of electrons is called current, and we'll talk more again about this in the next unit. But superconductors are unique. Superconductors are materials that have 0 resistance to current. What does that mean? Well, what we'll learn about is that when you have current is the flow of electrons. How many electrons are flowing past a certain point? How many charges are flowing past every second? How many coulombs of charge per second? That would be our current, how fast it's moving. Well, it turns out when current is flowing, when it comes to something that's not the wires, like a lamp or something called a resistor that will basically use the current flowing through it, current can eventually decay, and current can bounce against the atoms in the wire, and heat up the atoms instead of flowing through. And eventually, given enough time, if you just put current in and just walk away, you don't continue attaching a battery to it, current will die down pretty quickly. The electrons will stop flowing, they'll smack against things and give up their energy, their kinetic energy in the form of heat, and the whole current will stop. Well, it turns out there are certain materials, when you cool them down to extremely cold temperatures, and the first time this was ever found was in 1911. I believe his name was Onus. He cooled some wires down to 4 degrees Kelvin. That's 4 degrees above absolute zero. That is, in Fahrenheit, that would be about 455 degrees below zero Fahrenheit. He cooled it down, and what he found was eventually there was no resistance to flow. Current just kept flowing, and he just he added a little current to the system, didn't add any more, so there was no more battery attached to the current, and it kept on flowing indefinitely. And in fact, people have done experiments where they put a current into some materials that are superconducting, that are chilled down so that they have this property of zero resistance to current flow. And they have found experimentally, they've actually watched it not decay at all for 27 years. And in fact, based on their experiments, they calculate that it would stay without decaying for over 100,000 years. And some people believe that it actually would keep going for longer than the age of the universe. Okay, so this is an amazing discovery. And since then, people have worked on new materials that have absolutely no electrical resistance. So current will pass through the superconductor with no loss of energy. So you put current into a system, you use a battery or generator, put it in, and then you detach the battery or the current. You don't pump any more current in there, and the current will just keep flowing forever, theoretically forever, with no loss of energy. And it is a remarkable finding, and this is what's used in superconducting magnets, that might be used in the superconducting magnetic trains that are now being used in places like Japan, and experimentally being tested even in the US. So superconductors are materials that have absolutely zero resistance to current flow because there's no loss of energy to heat over time. And every year, somebody comes up with a new superconducting material where they don't have to cool it quite as high. And some of the best superconductors, they only have to cool them about 120 degrees below zero centigrade. Okay, those are the highest temperature ones that are normal superconducting materials that you don't have to do anything special to. You make the material, and if you go lower than minus 120 centigrade, the current will go on forever. But there are actually some even more amazing experimental materials where if you put certain substances under extraordinarily high pressures, and when I say high pressures, I mean 2 or 3 million times atmospheric pressure pushing on us. Unbelievable pressures. They've been able to make some materials act as superconductors at temperatures as high as just above freezing water. So close to room temperature. And that's the goal, that eventually somebody will define a superconducting material that will be superconducting at room temperature, that won't need to be cooled with special liquid nitrogen and liquid helium to get it down to super cold temperatures. And eventually we'll be able to have electricity that flows without any decay over time forever. So no heat loss happens with superconductors. All right, so charging. We've already talked about charging by friction and contact. So when we did the balloon on the cloth, the electrons due to friction, they're literally being scraped off of my Afghan blanket here onto my green rubber balloon. And the balloon being rubber and an insulator, the electrons just stay there. They don't flow all around the balloon. And now I have charged the balloon up, and I've charged the Afghan up. I've made the Afghan more positive. I made the balloon more negative. So examples of this would be if I take a negatively charged rod and place it in contact with a neutral object. So now you can actually transfer charge with friction and contact. So you make a rod charge. So you might make it charged by rubbing it with a cloth. It's now charged, and now I touch a neutral object and I can polarize a neutral object to make it make some of its electrons move to the neutral object. I can actually, when I touch the rod to the object, the electrons will jump to the object, especially if the object is made of a conducting material. If it's not made of a conducting material, it'll still jump, but it'll just stay right there if it's an insulator. But in any case, I can make electrons jump just by touching material. So you can make electrons jump from one negatively charged object to another neutral object by just tapping it, and the electrons will move to whatever is a more stable place to move. But you can also move electrons by doing things like stroking a cat. You stroke a cat's fur, or you comb your dry hair. I don't have any to speak of, but you comb dry hair, your hair will become charged because it's giving up its electrons to the comb. The comb becomes negative, your hair becomes positive. And if all your hairs are positive, positives repel positives, and that's why your hair will stick up all over the place on a dry winter day after you've combed or brushed it, from that static electricity of all the hair being the same charge and repelling each other. And if you now that you're charged, if you touch something with your hair, you can actually transfer the electrons from the other object to your hair to neutralize your hair. The easiest thing to do would be take water, so the water will pick up the charges and dissipate them easier. But you can transfer the charges. When you're walking in the winter on a carpeted floor, especially if you're walking with shoes on the floor, you're going to be transferring charges from the carpet to your shoes, and then you go and touch a doorknob, which is metal, and now you have some electric charge on you, and now you touch something that's very conductive. Those charges will leap from your hand to the doorknob and produce a spark, and that you can actually see. That's the air being ionized from the electricity from the electrons jumping a second you touch the doorknob. In fact, sometimes you don't even need to touch it. If you come close enough, the electrons have such a potential to want to jump. If you have a small enough distance, they'll just jump right away, and you'll see that spark. But that transfer of electrons is this contact charging of objects, either from rubbing or from touching. You can move electrons from one object to another and make the one that lost the electrons positive and the one that gained the electrons negative. But we have this other way that we've talked about called induction, and this is what happened when I took the charged balloon and put it on a neutral wall. The neutral wall then became polarized. The positive charges of the wall came forward and the negative charges of the wall went backwards, but the positive charges of the wall were close to the balloon, so the balloon stuck to the wall because the balloon was negatively charged. Well, the same thing can happen even at a distance. Charge interactions, just like gravity, can happen at a distance. These are forces that can happen at a distance. And later we'll find that magnetism does the same thing. These forces of electricity, magnetism, and gravity are forces that can happen over significant distances. Gravity happens over the longest distances, but the others can happen over smaller distances. So electrons, if you bring charged objects near a conducting surface, so in this case we have something like a cloud. And in clouds, especially storm clouds, you have particles falling inside the cloud. And these particles fall and they brush against other particles in the cloud, and they end up literally rubbing against it with friction, and they become charged. They'll leave one charge behind and they'll gain another charge. So the negatively charged particles, the particles that are falling pick up negative charges from the atoms around them as they're falling in the cloud. So the bottom of the cloud is filled with particles that have stolen electrons along the way of falling in the cloud. So the bottom of the cloud tends to be very negatively charged, and the top of the cloud has lost those electrons, and it becomes very positively charged. Well, now you have this giant thing overhead where the bottom of it, the part that's facing the ground, is negatively charged with enormous amounts of negative charge. So much that the force from that negative charge will reach down to the ground. There's so much electrical force as a result, it will affect the charges on the ground, on the earth, on the tops of buildings, on the tops of trees, on the tops of your head. And this is why when it's a really bad stormy night, especially if it's before it started raining and it hasn't quite done any lightning yet, you could actually feel kind of the hairs on your arms and the hairs on your head stand up a little bit. That's the polarization from the clouds above you because of all this polarization within the cloud. And now the negative charges are inducing the positive charges from the ground to be near it and repelling the negative charges from the ground down into the ground. So you now have polarized the earth itself, the top surface of the earth, the top of the buildings, the top of the trees, the top of the ground. And eventually, if you build up enough charge in the cloud, eventually that air between them will no longer be a good enough insulator. And the charge will jump from the cloud to the ground. And in the process, that's so much charge jumping that it's an enormous amount of electrons with enormous amounts of energy, so much energy that it essentially ionizes the air molecules as it's moving down to the ground so quickly. And that ionization is the lightning that we see. And then when we hear it cracking, that's the thunder that we hear. So a great example of induction can be done with insulated metal spheres. So these are spheres, we'll call them A and B. And these are metal balls, essentially, that are on insulated podiums, insulated stands. And the reason why they're insulated is to keep the charges from flowing down into the ground, down into the earth. Then the experiment would go away, essentially. So if you have two balls that are initially attached to one another, so they're acting as one giant double ball here, AB, in the beginning, it doesn't have any charge. We haven't done anything to it yet. And then you take a rod that you have purposely made a negative charge. It could be an amber rod that you had rubbed with silk, and now it's negatively charged. And so you've got this negatively charged rod. Well, if you bring it over to the balls, but do not touch the balls, you come near to it, it will start drawing the positive charge of the ball towards it and repelling the negative charges to the other side of these conducting spheres. The charges will surround the thing, but if you want to repel the negative charges, they'll end up on the back side of the other ball, and the positive charges will be close to the negative charge that you're bringing because opposites will attract and like charges will repel. So now B becomes negatively charged, A becomes positively charged because it's attracted to the rod. Now, at this point, you can physically separate the balls while you're still you have to still hold the amber rod next to A. If you pull it away, it all goes away. So you keep it next to A, and then you separate the rods. It requires a couple hands to do this. You separate the balls, not the rods. You separate the balls while A is still polarized. B is already polarized. There are no counter ions to balance the negative charges that are on B. The charges on B will stay on B. But now that you've moved B away from A and away from the rod, the charges from B can now spread out around B. So the negative charges will just completely cover the surface, the outer surface of B. There's no charge on the inside. The inside has zero electric field, but the outside's now loaded with negative charges. And A was polarized to be positive when you had the rod next to it. And since you've separated it from B, A is coated with positive charges. And the second you move the rod away, it does the positive charges aren't all held to one side, they spread out all over A. And now you have two balls, one that's positively charged all around the surface, on the outer surface, nothing on the inside, and one that's surrounded by negative charges all around the outer surface, nothing on the inside. And this process is how you can charge two metal spheres just using a simple amber rod that has been negatively charged to begin with, or you could have done this with a positive charge and you just switched the positive and negative of everything in this diagram, but you'll end up with the exact same result. This is induction. You are inducing charges to be formed by separating them, by polarizing things that weren't polarized before. Now, what's happening in the atoms? How is this polarization even happening? Well, the atom is composed of a nucleus where all the positive charges are, right in the tiny, tiny center in the middle of the atom. And it's got a cloud of electrons. And it could be one electron, but it still acts as a cloud because that point of electron, that single point charge of the electron, is everywhere at the same time. That's quantum mechanics. That's outside of this course, but essentially it's everywhere. Anywhere you look, you can find it in that volume of space. And you might have 1 electron, you might have 50, you might have 118 electrons. But you have that cloud of electron density, that negative charged cloud around a pinpoint area of the nucleus with all the little particles of the protons and neutrons. Neutrons don't have a charge, but the protons have positive charge in the nucleus. And if you looked at the positive charge, it's all right there in the center. But the negative charge is on average in the center too, because this is a sphere. So if the negative charge is evenly distributed all over the place, if you ask yourself, where's the center of the negative charge? It's in the same place as the positive charge, even though there's no negative charge at the positive charge. I don't know if that makes sense. But you have negative charge evenly distributed around it. So the average place, the center of negative charge, is the center of the atom, even though that's not where the electrons actually are. But if you polarize something, if you put, say in case B here, if you had something on the, say, the left side of that atom that was positively charged, the electrons would move over to be attracted to the positive charge, and so more of the electron density would end up being on the left side of this molecule, and less of the electron density would be on the right. Well, as a result, the right side would be partially positively charged, and the left side would be partially negatively charged. And this is what is happening in the quote-unquote polarization of an atom. You're literally taking each atom and kind of moving more of the negative over here and more of the positive over here, but it's still part of the same atom. And so it's the electrons buzzing around the the center of the negative cloud, which is normally in the same center as the nucleus, but just by geometry, it's the center of that sphere. They coincide, but in polarization, now those are separated, and you get this polarization. It doesn't have to be much to be effective, especially when you're doing this to millions or billions or quadrillions or quintillions or sextillions of atoms, enormous numbers of atoms. These charges will add up, and this effect will add up, and you'll end up getting a great deal of polarization. So you have what we call a partial negative charge on the left and a partial positive charge on the right. We use the lowercase delta, Greek letter delta. This is the lowercase d in the Greek alphabet to represent the term for partial. When you see that, it means a little bit, a partial negative charge and a partial positive charge. All right, so when you're doing polarization, if you have a charged rod that's negative, like that amber rod we talked about before, each of the atoms will start polarizing that's near it. So it's not like it's all the positive charge here and all the negative charge over here. It's that each atom tends to be more positive here and more negative here, but they add up to a total force that's more positive on one side and more negative on the other. It's all of these polarized atoms, we call them dipoles, so that all the dipoles will add up into one big dipole that behaves as if there was a lot of positive charge here and a lot of negative charge over here. And that's due to the attraction to the positive parts being pulled by the amber, and the repulsion by the negative parts being pushed away from the negative of the amber. So the positive and the negative will become they'll align. So each one will form a little dipole, a little polarized atom, negative and positive, negative and positive, negative and positive, and they'll all line up in the same direction, and you end up with this whole material that is polarized. And that's what happened with the balloon. That's what happened with the wall, especially when I brought the balloon near the wall. So when a positively charged comb, so this is a comb you've already run through your hair, and your hair stole the electrons from the comb, so the comb is now positively charged. If you took this comb that's positively charged, it's plastic, so it's an insulator. The charges will just stay where they started at. They won't spread all over the comb, just wherever you were brushing. If you bring that near a neutral piece of paper, a tiny flake of paper, and you can do this with paper, sometimes you can do this with other really light material, fur and feathers and things like that, something extremely light, and you bring the positively charged comb near it, it will cause the polarization of something that used to be neutral. The negative parts of that will move to one side, the positive parts will move to the other. In all the individual atoms, you'll get all these individual dipoles, and it will behave as if there's a lot of negative charge on one side of the paper and a lot of positive charge on the other side. And as a result, since the negative charge of that side of the paper is next to the comb, they will start attracting. The positive and negative will attract one another, and the comb will actually stick to the little flakes of paper or the little pieces of fur or feathers. And you can do this with any kind of light material as long as you can charge up some object and bring it in there. So the closeness will win. The opposite charges that are closer together have a greater force than the like charges that are further apart. Remember, moving it further apart makes that force much, much weaker. So the stronger force is the attractive one because those are the ones close to one another. The weaker force is the repulsive one because those are the forces that are far away from each other. And it doesn't take much extra distance to make the force go down. So it's making the repulsive force go down a lot and the attractive force go up a lot. So as we already mentioned, this is what happens with the balloon. You inflate the balloon, it becomes charged, and now it polarizes the wall itself. And that's why it sticks to the wall. This is because the charge of the balloon is inducing a polarization of the wall and making the positive part of the wall be closer to the negative part of the balloon, and then they will stick to one another as a result of this closeness with a positive attraction, an attractive force, which is actually the negative, and then the distant negative to negative is further apart, and that's the repulsion, but that's much, much weaker than this close attractive force. And that's why you can get any charged object to stick to any non-charged object. As a result, you're going to induce the uncharged object to become polarized. There are a lot of molecules that are already polarized by themselves without doing anything to them. Water is the most famous of these examples. Water is an extremely polar molecule. And if you look in your textbook, you'll see a positive charge on each of the hydrogens and a double negative charge on the oxygen. Now, this is not what's really there. It's started as that, but once these bonds are formed, it's not a full positive charge on the hydrogen and a full negative charge on the oxygen. They're actually partial charges. There's a little bit of positive on each hydrogen. There's a little bit of negative on the oxygen. And if you look at it in this orientation, there's more positive on the top of this molecule and more negative on the bottom of the molecule. So there is a polarization of the molecule. The electrons tend to be favored. They tend to be closer to the oxygen than they are to the hydrogen, and you end up with an electrically polarized molecule. So all of water is polarized. But normally, when you have a mix of water, every water is in a different orientation. So those polarizations are all pointing in different directions, and they kind of cancel out. But if you brought an electric field near it, a certain charge, you could polarize the water so they'd all be oriented in the same direction. But the distribution within the molecule is not exactly even because it's a bent molecule. But you will see more negative charge near the oxygen and more positive charge on the side that has the two hydrogens. So you can think of putting a line through here horizontally. The top would be positive, more positive. The bottom would be more negative. So we call these kinds of molecules dipoles, electric dipoles, or polar molecules. All right, so let's talk about electric field for a second. So electric field, like gravitational field, is kind of an aura of the field lines. And in the case of electric field, it's a measure of the force that affects other charges near it. So if we have a negative charge that's shown here, the electric field would be the force that something else feels it near this electric charge divided by its charge, the test charge that we're looking at, not the charge that's created. We're looking at some test charge that's nearby. If it's positive, it'll be a force that's attractive. It'll be pulling towards the negative. If it's a negative charge, it'll be a force pushing it away in the opposite direction, but the same magnitude of force. And if we take that force divided by the charge of that little object that's being affected by these field lines, that is called the field strength or the electric field. It's the charge, it's the force that's on it divided by the charge. Now, what force are we talking about? We're talking about the electric force, the force from Coulomb's law. That force divided by the charge that we're interested in that's somewhere near this thing. And when we draw field lines, we always draw the field lines into negative charges and away from positive charges. So because electric field or electric field strength is defined as force divided by charge, the units are force units divided by charge units. Well, our force units, like our weight units, are in newtons, and our charge units are in coulombs. So each coulomb is a lot of electrons, all right? So our field strength is in newtons per coulomb. And it turns out, like we've been saying, the field strength of this field, just like magnetic field and gravitational field, is dependent on the inverse square law. So just like any force field that we've talked about, it's inversely proportional to the distance squared. You increase the distance, the field strength will go down by the change in the distance squared. If you triple the distance, the field strength will go down 3 squared, 9-fold. If you shorten the distance, make it 1/3, you'll increase the field strength 9-fold. Whatever happens to one happens to the other opposite, but the field strength will happen to the square of what happens to the distance. So let's look at the field line direction. Okay, so the field lines are going to be in the same direction as the force on a positive charge. In other words, if we had some test small positive charge nearby either one of these charges that are shown here, a positive or negative charge, it's what would happen to that test positive charge. If we brought it near a positive charge shown on the left here, a big positive charge, you would feel force lines pushing it away from the positive charge. If we took that same little test positive charge and put it near the negative charge shown here, the lines are pulling it in towards the negative charge. So the field lines are always drawn for what would happen to some positive charge that we threw in near whatever else is there. So field lines always flow from positive to negative. It basically shows you what would happen to a positive charge. This goes back to Benjamin Franklin thinking that current was the movement of positive charges when we now know it's negative charges. So if you wanted to follow the force lines for a negative charge that was thrown in here, you would go in the opposite direction of whatever the arrows are. You would go away from the negatives and you would go towards the positives. And if you had a plate that was evenly positively charged and a plate that was evenly negatively charged, and this happens in a device called a capacitor, which we'll talk about in a little while, the field lines are all going right from the positive to the negative. So in the ends, there's a little bit of curve, but throughout the body of the plates, it's straight lines. The field lines and the force lines are pointing from the positive plate directly to the negative in parallel lines all the way through. All right, so here's Lori standing in front of a metal dome that is part of a device called a Van de Graaff generator. This was a device originally invented by Robert J. Van de Graaff in 1929 when he was working at Princeton, and then he spent most of his career working at MIT developing bigger and better Van de Graaff generators. So the Van de Graaff generator generates charge that is evenly distributed around the ball, the metal ball, and so if you touch it, now that charge is transferred, it's negative charge actually, and it's transferred to a person that touches the ball. So in this case, Lori is touching this, the charge literally runs up her arms, up to her hair, and since this is the outer part of her body, that becomes charged, and her hair now all becomes somewhat negatively charged. Well, negative charges repel negative charges, so all her hair is trying to repel against all the other hair, and that's why it stands up in all these directions. So let's talk about some related terms here. Electric potential energy. So unlike the electric field strength, now we're just talking about the energy involved here. Electric potential energy, it is a form of potential energy. It's stored energy based on the position of some charged particle near some other charged particles that have their own fields, either attractive or repulsive. So it's based on its position within that field. So the amount of potential energy to put it in that position is equal to the amount of work it takes to get it to that position and hold it in that position. You might be holding it in that position so that it's not repelled away from a like charge, or you might be holding it in that position so it's not attracted to an opposite charge, but it requires some work to get it there, and the amount of work you take to put it in that position is equal to its potential energy, the energy stored in that position. Because if you let it go, it's going to fly either towards the opposite charged particle, or it's going to fly away from the like charged particle. And this is the same thing you find when we have gravitational energy. You put in work to lift an object up, you raise it up, it has a certain amount of potential energy, and the second you let it go, it flies down to the ground, and because it has motion, it has kinetic energy, so the potential is turned into kinetic. Well, the same thing happens with a charge. If you're holding it in place, you did a lot of work to give it some potential energy and hold it in place. The second you let that charge go, it's going to fly either towards the opposite charge or fly away from the similar charge, but it's going to be moving, and that means it has kinetic energy. It lost its potential energy, and it's being converted to kinetic energy. So it's the same thing with if you had a spring. If you had a spring and you compressed it with your hand and you held it in place, it requires a certain amount of energy to do that. In other words, you had to apply a force and you had to move it a certain distance. Remember, force times distance is work. That's the work you put into it, and that work energy is exactly equal to the potential energy that's now stored in the spring. Well, the same thing happens when you're doing it with charges. If I have a big positive charge and I want to take a little test positive charge and move it towards that charge, it's being repelled. It takes work for me to do it. I have to apply a certain force, and I have to move it a certain distance to get it to a certain point near the other big positive charge. And that takes work. And the amount of work energy in joules, so it's force times the distance that I pushed it, that's the potential energy that object now has. If I release it, it'll fly away with a certain velocity, and then you can calculate its kinetic energy based on that. So in each case, we have to input work to get it into that position. We put in work energy. That work energy becomes potential energy until we let it go, and then it flies either away or towards to become kinetic energy. So in addition to electric field strength and electric potential energy, we have a third term that is very easy to confuse with the other two. This is a term called electric potential, not electric potential energy, just electric potential. And this term is also known as voltage. And I'm sure you've heard the term voltage. So what is electric potential? It is the potential energy that we just talked about divided by the charge of whatever object we're interested in. So it's the energy per charge. It's the potential energy per charge. It's the work we took to get a charge in a position divided by the charge of that particle that we just moved into that position. And it's usually electrons that we're talking about. So the formula is based on potential energy per charge. It's literally taking the potential energy, that is the work that it took to get that particle in position, divided by its charge. So the voltage, the electric potential, these are the same thing. They mean exactly the same. It's not the same as the potential energy. This is potential energy divided by charge. It's per charge. The voltage is equal to the potential energy divided by the charge. Now, what does this mean? It means the voltage is directly proportional to the potential energy. Increase one, you'll increase the other by the same amount. Decrease one, you'll decrease the other by the same amount. But it's inversely proportional to the charge. If you increase the charge, you will decrease the voltage or electric potential. If you decrease the charge, you will increase the voltage. Why? Because now you have more energy per smaller charge. So you will have more voltage. Okay, so keep these proportionalities in mind. It's proportional to the energy. It's inversely proportional to the charge. All right, so if we have a situation with a ball that's covered with positive charges, and we have two charges that might be affected by it, one that has a little bit of positive charge and one that has a lot. They both will feel potential energy of being repelled away from this the bigger ball position. It required a lot of work to get each of these in place, but it required much more work to get the bigger one on the right, on the bottom of the two, close to the big ball, than it did for the top one because it has less charge. But if we took the energy it took for each of those and divided it by how much charge each one has, we find that we have exactly the same ratio of energy to charge, and therefore they have exactly the same electric potential. That's the same as saying they have exactly the same voltage. They have the same amount of energy per charge that they are carrying. And because electric potential or voltage is a measure of energy per charge, it's in units of energy units divided by charge units. Our energy units are joules. Our charge units are coulombs. Remember, coulomb is a lot of electrons, 6 times 10 to the 18 electrons, but it is our unit of charge. Well, a joule divided by a coulomb, that's the unit we use, has been given the name volt in honor of Volta, another scientist that was made famous for working on some of the first batteries. So a volt is the same thing as a joule per coulomb. It is the unit that we use for electric potential. It is the unit we use for voltage, which is the same thing. So keeping in mind the formula that voltage or electric potential equals potential energy divided by charge, if we double the charge, so that's in the denominator, we double the charge, but we keep the same potential energy. Remember, we're not touching the potential energy, we're doubling the charge, but the charge is inversely proportional to the voltage. So if we increase the charge twofold, we will decrease the voltage twofold, so the voltage will become half of the original voltage. If we double the charge and we double the potential energy, so we're doubling the numerator, the potential energy, and we're doubling the denominator, well, the doubles and the doubles will cancel each other out. One makes it go up twofold, and the other makes it go down twofold. It cancels out, so you end up with exactly the same voltage. So if you do the same thing to the charge and the energy simultaneously, you will end up with exactly the same voltage every time. Because voltage, just like this diagram at the top shows, that the same larger object with the same object with more charges on it will require more energy to be near this big object on the left here, this big ball with positive charges. So because they require the same amount of energy per charges that they have the same voltage applied to them. So electric potential energy is measured in joules. Anything energy is measured in joules. Work energy, potential energy, kinetic energy, heat, those are all in joules. Electric potential, specifically the potential energy per charge, in other words, potential energy divided by charge, on the other hand, is measured in volts, watts, amperes, or in joules as well. Well, we already know electric potential, which is potential energy divided by charge, is also called voltage. But electric potential is voltage. We measure it in volts. Joules per coulomb is a volt. So volt is the answer. It's the unit for electric potential because voltage is another name for electric potential. Don't confuse it with just the potential energy. That is an energy unit, joules. Watts we already know is a unit of power. Joules we already know is a unit of energy. Amperes is something you haven't seen yet. That's a unit of current. That's actually a unit of charges per time that are flowing through a wire, but we'll discuss that in the next unit. So since you're measuring electric potential energy per charge, your units are energy units divided by charge units, joules per coulomb, and we call joules per coulomb volts. Remember, voltage or potential or electric potential is potential energy divided by charge, PE over Q. And the volts are energy unit, joules divided by coulombs are charge unit. All right, so electric potential, otherwise known as voltage, so high voltage at very high electric potential energy. So we have a large potential energy and a large amount of charge. If the potential energy is very, very large, even if we have a lot of charge, the numerator divided by the denominator will still end up being a large voltage. So we're taking a gigantic number and dividing it by a large number. We'll still end up with a large number, a high voltage. But you can also get high voltage by taking a low number, a low energy, and dividing it by a super low charge. And this is why we can have actual charged balloons that carry 5,000 volts of voltage, of electric potential. You might go, I can't touch something with 5,000 volts. Yes, you can, as long as it's 5,000 volts. Remember, volts is a ratio. It's a ratio of energy to charge. If both of those numbers are small, if the energy is small and the charge is super small, you get a small number divided by a super small number, you'll get a big number too. And that's what happens with a balloon. You have a tiny amount of energy. So if I have a balloon that has a potential energy of only 0.005 joules, and I have 1 times 10 to the minus 6, that's a millionth of a coulomb. Well, if I divide those two, I divide 0.05 joules divided by a millionth of a coulomb, I'll get 5,000 volts. That sounds like a lot of volts. It is a lot of volts, but it's a lot of volts due to a tiny amount of energy and a super tiny amount of charges. Remember, a coulomb is a lot of charges, but a millionth of a coulomb is still a lot of charges, but in the realm of things, this would work out to about a trillion charges. That sounds like a big number, but a trillion charges, a millionth of a coulomb is a trillion charges, 6 trillion charges, I should say. That's still a small amount because remember, atoms are insanely tiny. There are many, many, many more than 6 trillion atoms in this balloon. So making 6 trillion charges is nothing compared to all the atoms in the balloon. So this is actually a very small amount of charge. This is why we use the unit coulomb, because it's so many charges, because a lot of charges really isn't that much charge. So in this case, we have a little bit of energy divided by a really little bit of charge, and we end up with a big ratio, a big number of volts. You can also get high volts because you have high energy, like these high tension wires that carry enormous amounts of electricity above our heads. There it's a lot of charge, but it's even more energy, and therefore that high voltage really is dangerous in those cases. All right, so electric storage, let's talk about this. So electricity usually frequently has to be stored somehow, and one of the easiest ways to store it is in something called the capacitor. A capacitor is essentially 2 plates, one attached to the positive terminal of a battery or a generator, and one attached to the negative terminal. And if you let this thing flow current through it over time, the electrons from the positive plate will flow gradually through from the plate, through the wire, through the battery, to the negatively charged plate. So you have to give it a certain amount of time, and you'll build up negative charge on one plate and positive charge on another plate. And the simplest capacitor is just a pair of conducting plates that are separated by something. They're separated with some distance, and the bigger the plate, the better it will be at storing charge, and the closer they are together, the better it is as well, the more you can store. So as long as there's no path to discharge between the two, as long as the air is between them to stop them, or there's some insulating material between them, what we call a dielectric, something keeping the charges from hopping from the negative to the positive plate, that is a way to store up energy, and you can store tremendous amounts of energy. Now in practice, these capacitors can be really big, like in old TVs, or they can be really small and very flexible. So you have a foil that's holding the negative charge and another piece of foil holding the positive charge, and you put a piece of paper in between, and you can actually roll them up tight. So the whole capacitor is actually a little roll that'll fit in a little device about that big. So it doesn't look flat. It's actually kind of rolled up where they're still separated. The charges can't hop from one plate to the other. And because they have no path to discharge, the voltage will remain high. If you let this run long enough, the voltage between the two plates will be exactly the same voltage as with the battery. So if you start with a 12-volt battery, you'll have a 12 volts of voltage between the two plates. But the plates are big, and they can hold a lot of charge. So a lot of charge means a lot of energy, and you can store amazing amounts of energy, and these things are used when you need to produce a huge amount of energy fast. If you just waited on a battery to produce enough energy, you'd have to wait for the battery to slowly move electrons and move energy through the circuit. But capacitors can hold huge amounts of charge, and all you have to do is connect them one end to the other with some kind of connecting wire, and the charges, boom, immediately switch from one to the other, and huge amounts of energy can be released instantly. And that's why they're used in flashes for cameras, camera flashes. If you need an enormous amount of energy to produce a huge burst of light, capacitors are used to store up charges. That's why you're waiting for your camera to store up charge. With the older style cameras, you're waiting for the battery to pump in enough electrons to make the plates charge. It has a huge amount of charge, then you connect the plates, and bam, all that energy is released, and you get this bright flash from the light bulb that it's attached to. But they also use these in old TVs that use vacuum tubes. The problem is they build up so much charge in these old devices that even if you turn the TV off for days or even years, it will still hold the charge. There's nothing that allowed the charge to flop over, even when the TV was turned off. And people have died from touching the capacitor long after the TV was turned off because this enormous amount of energy was then transferred into their body. All right, so electric storage happens because the positive charge of the battery, the positive terminal, pulling electrons away, and the negative terminal is pushing electrons towards the negative charge plate of the capacitor. And eventually you have these oppositely charged plates that have enormous amounts of charge, but if you added up all the charge, it would be zero. The amount of negative charges is exactly equal to the positive charges, so the net charge on this device is a zero. All right, so the charging process is complete when the potential energy between the plates equals the potential between the plates equals the potential difference of the battery terminals. That's another way of saying the voltage of the plates will eventually become the voltage of the battery. So the greater the battery voltage, the greater you can make, the greater the voltage you can make on the plates. And if you make the plates closer, it's better. If you make them larger, you can really store a lot of electrons on the negative plate and a lot of positive charge on the positive plate. And it's enormous amounts of energy that can be stored that can all be released in a blink of an eye. And like I said, large capacitors can kill a human being. So you have to be extraordinarily careful with these. Make sure that you're not the conducting path to let that release its energy. And one last device we're going to talk about, we mentioned the Van de Graaff generator. I just want to show you how this works. So what it is there's a motor on the bottom that drives a big belt that runs up a tower. And the tower can be desk high, or it can be 30 feet high or more. I think the biggest one is about 37 feet high. And there's a giant metal ball at the top of this thing. And this roller, the rotor at the bottom is rolling a conveyor belt that's made of rubber. Rubber's an insulator. Well, at the bottom, there's a voltage source that's adding charge, adding electrons to the, and it's actually transferring it where it says the metal points at the bottom. It's transferring it directly to the rubber belt that's rolling up and down this thing around in a big loop. And because rubber is an insulator, when you put charges on the rubber, it stays in place, but the belt is moving. So it literally carries these negative charges that are added to the rubber up to the top. And at the top, there's another metal comb that will brush against the rubber belt. So as soon as those charges are carried to the metal, it just transfers to the metal conductor at the top. That's where it says metal collector points. And the second those electrons reach the metal point, it just spreads all over the surface of this giant metal ball. And now it's on the outside, and you can build up enormous amounts of negative charge on there. And the Van de Graaff generators have a theoretical maximum of 7 million volts that you can generate from just a small voltage at the bottom. But you're just pumping charge. You're pumping negative charge up that eventually just keeps coating the top. And eventually there's a limit, but you can only get so much up there. But you can get the biggest generators typically will carry up to 2 million volts, but theoretically they can carry up to 7, especially the double ones. And while you have enormous amounts of charge on the outside, enormous amounts of voltage, electric potential on the outside of these Van de Graaff generator balls, the charge on the inside is absolutely zero. There is zero electric field on the inside of the ball. And in fact, if you build cages, metal cages where people can stay inside at the bottom, when these things start generating giant lightning bolts coming down from the top of the generator, people inside these cages, they're called Faraday cages, are completely safe because any charge that hits them will just surround the outside of their cage and never enter the inside. There'll be no electric field on the inside of the cage. So let's see. So here's a picture of the world's largest Van de Graaff generator. It's a double generator. It's in the Boston Museum of Science, and this was actually built by Robert J. Van de Graaff himself while working at MIT. And he spent most of his career at MIT. And he actually left behind another Van de Graaff generator at MIT as well. But this is the largest one. It's across the river in Boston. And you could actually go and see demonstrations, and you can see these giant lightning bolts in the bottom picture being produced. When the charge builds up so much, it has to be released. And the air, no matter how good an insulator it is, will allow the electric charge to come through, just like clouds will eventually produce lightning bolts because so much charge is built up on the cloud, and eventually it'll be released to come down to the ground. So the lesson here is if you pump enough voltage in a cloud or in a Van de Graaff generator, air being a wonderful insulator, eventually even air will become a conductor of electricity. So let's play a little demonstration here so we can take a look at what an actual Van de Graaff generator looks like. We're going to switch over.
This Van de Graaff generator is the largest of its kind in the world, and you can only find it at the Museum of Science in Boston. In fact, it was built by Robert Van de Graaff himself. It's 37 feet tall and can generate 2 million volts of static electricity. That means some pretty big sparks. Believe it or not, both of these Van de Graaff generators work the same way as the old sneaker in the carpet routine. But instead of rubber sneakers, there's a rubber belt. That brings the static electricity to the top of this ball. It builds up until finally it jumps to the ground. Now this one uses a small belt, but our 37-foot Van de Graaff generator has a really big belt. We're talking 4 feet wide. So I got a secret for you. No one has ever seen electricity. You can't see it. I know what you're thinking. I saw a spark. That's electricity. But not really. It's electrons traveling so fast through the air that they actually superheat the air and you see a glow. Sort of like this. Now, if you want to learn more about electricity, you can visit sciencebob.com. If you want to see this thing in action, you can visit the Museum of Science in Boston.
So let's stop that here. And with that, we'll end the unit.